Bismillahirrahmanirrahim. So let's start with today's lecture. Today's lecture is about design of shafts, and as we have discussed in the class, this is one of the most important machine element. And in today's lecture, we'll see the design of the shafts based on the torsional load as well as the bending loads, and how these loads affect the design or the diameter of the shafts. So this chapter is from this topic is from chapter number 14 from Khurmi or chapter number 7 from Shigle. So let's first define what is the shaft. Difference between shaft and an axle. Shaft is basically a rotating member. It's actually a circular cross section. It's used to transmit power. The basic difference between shaft and axle is the shaft is generally used to transmit power or torque, whereas axle is the shape of the axle and shaft is exactly the same, but axle is generally non-rotating. It is non-rotating and supports the rotation elements like bearings, like other elements, pulleys or like this. But shafts can carry power transmitting element like gears, pulleys, flywheels, cranks, sprockets, and other kinds of elements. Shaft, the elements that can be mounted on the shaft are gears, pulleys also termed as sheaves, flywheels, clutches, couplings, sprockets, and a lot of other elements that are used to transmit power. And these elements usually combined by either press fit or by using keys, pins, and splines. Whereas the bearings and retaining rings are used to support the shaft, and retaining rings especially are used to actually restrict the motion of element on the shaft, so that element will not slide on the shaft while there is a power transmission from one point to the other point. So as far as shaft stresses are concerned, the shaft is actually subjected to three kind of stresses: bending, torsion, and axial stress. But in this case, we only focusing on two type of stress, that is the bending stress and the torsional stress. In very rare cases, we have an experience, the shaft experiences axial stress, like in drill bits. A drill bit actually, if you remember, you have a bit and you're drilling it, so actually a force is applied axially to the shaft. Similarly, so we have the application of propeller shaft in ships, so they experiences the axial loading. But there again few very specialized application in which shaft actually experiences axial loads. But generally in most of the applications, shaft actually experience bending and torsional loads. So materials are defined based on high strength, good machinability, low notch sensitivity factor, good heat transfer properties, and high wear resistant properties. As we are talking about that, in very rare cases, the axial stresses are applied on the shaft. So generally, we are focusing on two types of stresses: shear stresses and bending stresses. Shear stresses are generally due to the torque that is transmitted to the shaft. Actually, what happens is you have a motor, for example, and let's say this is a motor and this is a pump. You want to transmit power, so you have to require shaft for that. So there's a coupling in between, but in order to transmit power from A to B and from motor to pump, you require shafts. So shafts generally rotates and they transmit torque. But because of the weight of the shaft and probably this, let's say this coupling, there will be the bending load on the shaft due to the weight as well as the elements mounted on it. So shaft can be subjected to combination of both kinds of load, that is torsion load and bending loads. As we have discussed about the difference, so the slide suggests this. The shaft can also be subjected to torsion load individually. Yes, it cannot be subjected to bending load only, because bending is applied due to the elements mounted on it, and generally when this happens, the shaft actually is rotating. So that's why you can have a case where there is only a torsion load, and you have a second case where we have both kinds of loads. Clear? So one case is torsional load only, and the second case is the combination of torsional and bending load. Okay? So we can have only two cases. As far as the standard are concerned, the stresses can be calculated from ASME standards. So ASME standard says if you want to find the allowable normal stress, which is this is actually the allowable stress. So in case of the normal stress, you can either calculate zero point 0.6 of sigma y, which is called yield strength, or 0.36 of sigma u, whichever is less. So you have to calculate both values, and whichever the value is less, you have to use that value for your design. Similarly, if you want to find the allowable shear stress, which is this, then the formula will be half of this. You can see the tau will be zero point 0.3 of sigma y or 0.18 of sigma u. Again, if you need say normal stress, you have to use this combination, and if you have to find the shear stress, you have to use this combination. When shaft is directed to only torsional load, like in solid shafts, what we have is tau is equal to, this is a very famous relation from mechanics of materials 1. Very famous relation. And you remember there is another relation called G theta by L. So in case of torsional load in shaft, we have to use this formula, tau is equal to T over J, where tau is the shear stress, torsional shear stress, R is the radius of the shaft, T is the torque applied on the shaft, and J is the polar moment of inertia of the shafts. So you know that this is tau allowable. This R is nothing but d by 2. This torque is actually the same as we have used here, and J is nothing but pi by 32 d4. Putting all those values, taking d as our design parameter, we end up d equals to cube root of 16t over pi tau allowable. So if you know the torque in the shaft, and if you know the material of the shaft, you can actually find the diameter of the shaft that is used to transmit torque. But if you have a torque shaft that is hollow, generally in case of heavy vehicle, we use propeller shaft that is hollow. Hollow shaft has an advantage of transmitting high torque as compared to a solid shaft. So only difference with the previous formula is, if you I writing again the formula, the only difference in this case is outer diameter, because the hollow shaft has two diameters. One is the outer diameter, which is d naught, and one is the inner diameter, which is di. So the r is the outer diameter, and j is defined as pi by 32 d outer 4 minus d inner 4. So if we have a solid shaft that di is equals to 0, we end up with the same formula as d naught become d, and this becomes 0. We again get pi by 2 d4. So in case of hollow shaft, the only difference in the relation is that the r, which is radius of the shaft, can be written as the outer diameter of shaft divided by 2, and j is actually the polar moment of inertia of the section, which is the outer 4 minus the inner 4. And if you want to design the shaft based on rigidity, you have the formula of T over G theta by. Rigidity means you have to use modulus of rigidity or shear modulus, and based on that you can design the shaft. This is the cases in which generally the material is not defined, so you can use material is defined in the case of shear modulus, not in the case of allowable stress, so you can actually design the stress based on the rigidity. So, but these are very few cases in which you have to use this approach. So this is the problem, very simple problem, in which you have to find the diameter of the shaft. So we know that the diameter of shaft, as we know, is 16 t over pi tau allowable. So we know that the torque is, so now power is given and RPM is given. This is your RPM and this is your power. So simple thing is power is equals to 2 pi nt by 60. So torque can be defined as 60 p over 2 pi n. So we have to find from 60 into the power is 20 kilowatt, which is 20 to the power 3, divided by 2 into pi, and you have to put RPM, which is 200. So whatever the answer is, you have to put that value right here, and the allowable stress is 42. So you have to write this here, and this will be written as 42 into 10 to the power 6. You get the diameter, whatever that is. So this is the idea of calculating the diameter of the shaft. This is another formula in which the torque exceeding the mean torque. So first we have to find the torque based on the power and the RPM. So this is your power, this is your RPM. So we know that T is equals to 60 P over 2 pi N, where 60 into power is 1 megawatt. 1 megawatt is written as 1 to the power 6 divided by 2 into pi into this is 240. So whatever the answer is, so this is called your torque, and your maximum torque is actually equals to 1.2 of T. So it when you multiply, because it's actually 20 exceeding 20%, so we have 1 plus zero point 0.2 is the 20% factor. So again the rest is the same. You have to use same D formula, D equals cube root wala formula to use the to design the diameter of shaft. This is the third case in which we have a hollow shaft, and I'm not solving it because these are the very fundamental problem. We are going towards the more complicated problem later in this lecture. So in this case we have a hollow shaft, so we know that the ratio of inside and outside diameter is, so we can say di over do is equals to 0.5. So in this case you can say that di is equals to 0.5 of d naught. So using this formula we know that d tau over r, which is d naught by 2 divided by t over pi by 32 d outer 4 minus d inner 4. So when I put di in do, so this can be written as 0.5 d naught square. So all of the values will be then converted into d outer. So first we will find d outer, and then using this formula we can find the inner diameter. So we can find both diameters based on this scheme. So I'm not solving it again, just to give you an idea that how we are going to solve these problems. Now, when you have any element on the shaft is actually subjected to, you can say, the bending load, and that bending load is actually, you can see here, these are the bending loads. So this is actually applied because of the elements like gear, pulleys, or sprockets mounted on the shaft. So you have bending loads, and these bending loads actually is applied on the shaft in order to what you can say in order to design the shaft. So we have torsion load, which is represented here like this, and we have bending load, which is transverse load, which is written as here. So in our case we have both loads combined together. So this is some, I'm going to the slide. This is some of the idea that how we can develop the formula if we have the bending load as well as the torsion load. We use the Mohr circle and the idea of principal stresses to find the relation. So this is the Mohr circle, and these are the two relations for the principal stresses. The principal stresses, by the way, if you remember from mechanics of material 2, these principal stresses are basically the maximum normal stresses that can exist in an element. The stress in the element cannot exceed the normal or principal stress of this element. So by using this relation, we end up with what is called as the design relation for shafts containing both torsion and bending load, and the relation is nothing but, if just give an idea, the relation is if I just convert it, the final relation is V is equals to cube root of 16 under root of m square plus t square divided by pi tau allowable. This is the relation that you can say, this is a relation that contains both torsional as well as bending loads. So you can see that if I put bending moment equals to the bending moment, we end up with 16t over pi tau allowable, which is the same relation as with the solid shaft without any bending load. So in this lecture, we will focus on the problem that contains both bending load as well as the torsional load. So these are certain few slides that you can consume in order to understand how we develop relations. This is one of the formula in which the bending load moments are given, and then you can find. So I'm not solving these problems because later on we will be actually finding all these bending moments, and then we'll be able to design the shaft. So what you have is, in case of shafts, you you have the bending loads due to gear. So in case of gears, so spur gear, we use only spur gear for this DME1 course. So we have two types of forces. So we have a line that is actually passing through this tangent to the base circle of the gear, and we have W1, which is called normal force. So this is actually inclined certain angle, and the angle between the Wn and Wt is called the pressure angle of the gear. That's normally given, and this it can be resolved into two components. One is called Wt, second is called Wn. Wt is the tangential component, and Wr is called the radial component. Here, so this is the two components that are important, that are actually contributing towards the bending of the shafts. So WT is the driving force of the gear, which is written as torque over radius, and this formula is nothing but T is equals to Fr. Whereas WR is equals to, which is called radial force of the gear, is equals to WT tan phi. Again, phi is the pressure angle of the gear. And when we'll solving the problem, you will see how we calculate those forces. Similarly, in case of chain sprocket, because chain sprocket is also one of the power transmitting element, in case of chain sprocket, we have a sprocket and a chain, and chain has two sides, one is tight side and one is slack side. Generally, in case of chain sprocket, the tight side has we use all the force and slack side is equals to 0. So we have driving force of the chain sprocket is equals to torque over radius of the sprocket, and then if the force is at a certain angle like 10 or 20 degree or whatever the angle is, we have to resolve into rectangular components. This is also written like this. In case of V belts, third element is called V belts. In case of V belts, we have two pulleys again, but in V belts, the slack side force is not equal to 0, it's less than 0. Generally, the slack side force is almost 1 by 5th of the tight side force. So F1 is the tight side force, F2 is the slack side force. So the driving force of the pulley is written as T over D by 2, whereas the bending force of the pulley is 1.5 times the normal force, the driving force. So this FB is actually responsible for applying the bending load on the shafts. So again, this is the same pulley relation. So we have tight side and slack side, and the forces on the tight side generally higher and the slack side generally lower. So let's directly jump to a problem. So this is the problem that we're going to solve in this lecture today, and these are kind of similar problem that you will experience in your exams. This is, by the way, is the problem from the last final exam of DME1 from 2K20 batch, and sorry, 2K21 batch. This if you look at the problem, so problem says analyze and design a step shaft 2. So we have a step shaft 2 here, although the diagram is not step but actually it's a step shaft used to transmit used in the power transmission system that drives a lightweight conveyor as shown in the figure. So what happens is you have a motor that is serve as a drive source for the power source. The power comes here, passes through a pulley V belt, then transfers to the shaft 2. Shaft 2 contains a pinion gear. This gear transmits the power to the bigger gear, and bigger gear is the shaft is connected to a light conveyor. So the idea of this kind of the assembly is that in case of conveyor belts, we have to reduce the speed of the conveyor. So we use a speed reduction mechanism, or in other words, you can say torque conversion mechanism, in which we reduces the power, reduces the RPM of the shafts in order to enhance the torque of the shaft, or the so power, or in simple word, not to enhance the power load lifting capability of the conveyor. But always remember, this is very important point, that you cannot increase the power. Power remains the same throughout the system. Actually, in fact, it actually there is a losses in the power transmission. The only difference is, and that's very important to highlight here, is that you can enhance the torque, you can increase the torque at the expense of RPM. So when RPM is increased, the torque will be decreased, and if the RPM is decreased, the torque will be increased, but the power remains the same. This is the idea behind this. So what happens is, so the motor is 4.5 kilowatt, shaft to the RPM of 1100. So we all dimensions are given. You have to design this step shaft, which means we have to find diameters at 4 locations, here, and here. So now we'll start solving these problems, and because this is the problem for final exam, so these similar kind of problem you will experience in the exam. So let's jump towards the sorry. So let's jump towards the solution. So I've just draw it again. So we have power equals to 4.5 kilowatt. So in order to convert power, okay. First we will write the data. So first we will draw the free body diagram. So in free body diagram, so what I have here, sorry, I've just used line. So this is the line. So we have point A, we have point B, we have point C, and we have point D. The point A, if you see the problem statement, the point A contains the bearing, so we call it B1. So we have a bearing here. Bearing can be represented symbolically as this. The B2 contains the pulley, so we have to draw pulley here. So this is your pulley, and you have a belt at a certain angle, and this angle is defined as 60 degree in the problem. So this is your pulley, and then you have the gear. So you have a bearing 2. So this is your B2 at this point, and on third we have a gear. So we have a smaller gear, and then we have a larger gear. This is your larger gear. So this is your pinion. This is your bigger gear. Clear? So this is the problem crux. Now the first thing that you have to do is to draw forces, the action forces or the bending forces of these two elements, pulley and the gear. So first of all, using different color, I have to use. So what we have here is the force can be translated here as FB, which is the bending force of the pulley. So because 60-degree angle, we have two forces. One is this force and one is this force. This force is FB cos theta or cos 60 degree, and this is FB sin 60 degree. Clear? FB cos 60 degree and FB sin 60 degree. Similarly, in case of gears, as we are discussing in the gear section, there is a line that passes tangentially to the base circle. So this is the line that you have to pass through it, and there is a horizontal line, that is this. So angle between the horizontal line and this tangential line is called the pressure angle of the gear, which is phi. This is the case when the gears are upside down, or you can say up, top and bottom. When their gears are sideways like this, so the line will be like this, and the pressure angle will be like this. So keep remember, there could be two configuration, one in which one gear is in the lower side or upper side, or second in the lower side or upper side, and we have the second case is side by side gear configuration. So this is called WN, as we have seen it, WN. So that is very important to see in which direction this is moving. If you look at the figure, this is moving in the anti-clockwise direction. The gear will also move in the anti-clockwise direction. So based on this gear, the force will be in this direction. So here, this is the action gear, WN. So this direction actually is because of this rotation. Rotating otherwise, so it will be like this. Clear? So WN, so we have pressure angle here also. So we have two forces, one is this and one is this. The force that is actually tangent to this circle is called as WT, which is tangential line, and what is radially, this is actually along the towards the radius, this is called WR. Similar is the case, so this is called action triangle. So we have similar triangle here. So this component is called WT and this component is called WN. Sorry, not W1, WR. So what we have here is this is called action triangle. This is called the action triangle, and this is called the reaction triangle. And we know that these two triangles actually is formed because of the rotation of these gears. Now we know now the forces of these two elements. Again, in case of pulley, you have to see in which direction a pulley could be like this. You have a pulley which could be like this. So we have to use this, and then we can draw cos and sine components. So it could be at any angle. It could be sprocket as well. So in in case of sprocket and pulleys, belt pulley system, the forces are defined on the same principle, that is, in which direction the belt is, at which angle with respect to horizontal or vertical the belt is moving, you can draw the angle. But in case of gears, the different configuration is used. That is, you have to use the draw a normal line which is passing tangential to the base circle, and then we have two component. One is called the radial component, second is called the tangential component, and we have to draw like this. So below this diagram, so we have to draw a line so that we can make the components. So here, so just for the sake of simplicity, we know these are direction forces out there. So we are written as RB1Y. This is RB1X. Similarly, we have RB2Y, and this is RB2X. So one can argue that how we know the direction of these reactions. So as you know from your statics course, from your first year, that direction doesn't make any difference. Uh, it's only that your reactions, you have to draw the direction, whatever the direction of the reactions are. If your forces direction are okay, it's okay, they are correct, the forces are correct in the right direction, then only your reaction will be automatically correct itself if you have drawn the wrong direction. So by using this, you have to split this free body diagram into two parts. One is called the horizontal plane, second is called the vertical plane. The idea is to separate forces in the horizontal and vertical plane. Now it's very difficult to draw forces in the horizontal because they are in the horizontal. So what we take assumption that whatever the in the right direction will be written downward as positive. So whatever force that is in the right direction, right from left to right, as positive will be drawn on this horizontal plane as upside down. So if you look at this force R1Bx, because it's an horizontal force, but its right side, so it is written as like this. So this force is RB1X. Hopefully you have actually understood this. So you actually flip this force, so you can draw it on the horizontal plane. So this is your first force, that is this. The second force is actually like this in the opposite direction. So because of this opposite direction, so we can draw force in opposite direction as well. So this is FB, and this is cos 60 degree. The third case, if you look at the horizontal force, which is this is a tangential component. Okay, one very important concept here: which triangle to be taken, either action or reaction triangle. So my idea is that the with the force which is actually acting towards the shaft, the radial force, the triangle in which the radial force is actually directed towards the shaft, that triangle should be used. Although in different books there are different concepts, or there could be a difference in different books, but my analysis from 8 to 10 books concludes that you have to take a triangle, because there are two triangles. You have to take those triangle direction in which the radial force is acting towards the shaft. So if this is the force and it is in line with the RB1x, so written as WT. And the last force, which is this RB2x, is actually opposite to RB1x, so we have to write like RB2x. So hopefully you have actually understood the idea of writing those forces. Now in case of vertical forces, the idea is very simple. Just write topward is positive. So this is RB1y. So this force is actually upward. So again we write it as FB sine of 60 degree. In the third part, what we have is this is actually downward, and downward is taken as negative. So we have this direction which is WR, and the last force is actually upward, and upward is the same direction as this. So this is taken as positive. So this is RB2Y. So this is two forces in two planes. One is the horizontal plane, second is the vertical plane. Now, based on this analysis, now we have to calculate these forces. Now, your most of the mechanics of material concept will be applied now. Okay. The first step is to find the torque. So torque is 60p over 2 pi n. 60 into the torque power is 4.5 into 10 to the power 3 divided by 2 into pi, and the n in the rotation is 1100. So the answer is 39.1 Newton meter. So torque on this shaft is 39.1, and you have to remember that this torque is at every point on the shaft, at the gear, at the pulley, everywhere on the shaft the torque will be 39.1 Newton meter. The second step is to find forces, magnitude of the forces. So first let's start with the pulley. So we know that pulley has a driving force Pn equals to T over dP by 2, where dP is the diameter of pulley. This is 39.1 divided by what is the diameter of pulley? From the numerical, if you look at the numerical, the diameter of pulley is written as 254 mm. So because it's Newton meter, so I have to use 254 into 10 to the power minus 3, which is again meters divided by 2. So then the driving force of the pulley is 153.9 Newton. Okay. So now from the previous theory we know that we require is the bending force, and the bending force is equals to 1.5 times the driving force. That is 1.5 times the normal force is 153.9. So the answer is 230.9 Newton meter. Sorry, not Newton meter, sorry. It's only Newton. Okay. So now we can say that FB, now it's very simple, you can write like this. FB cos of 60 degrees, FB cos of 60 degrees equals to 230.9 into cos of 60. So the answer is 115.5 Newton. Similarly, FB sine 60 degree equals to 230.9 into sine of 60 degree. So the answer is 200 Newton. So what we have is, now we know the forces, two forces. This is equals to 115.5 and this is equals to 200. Okay. Taking to the next page, we have to find forces on the gear. So for gear, we know that the tangential force is the driving force, which is equals to torque over dg by 2. What is dg again? It's a diameter of the gear, or the pitch diameter of the gear. So from the problem, we see this is 39.1, and we know the diameter of the gear given in the problem is 133 mm. So 10 to the power minus 3, because convert into meters. So you end up with the answer of 294 Newton. This is tangential force. So the radial force equals to, based on this triangle, so we know that this triangle, if I isolate this triangle here, so we have, this is called WR, this is called WT, this is called WN, this is called phi. So we know that tan phi equals to WR over WT. So what is WR equals to? Definitely equals to WT tan phi. So WR is equals to WT tan phi. WT is 294 into tan of 17 degrees. Tan of 17 degrees. So the answer is 89.9 Newton. Now we know the forces. So just write before, WT is Wt here is 294 and Wr is 89.9. So because we know the forces, now we have to find reactions. So finding reactions, if you look at here, first of all, horizontal plane. So look at the horizontal plane. Clear? So we know that RB downward positive, RB plus RB1x, RB1x plus WT in the horizontal plane, taking downward as positive, equals to 0. So this is WT, and with the minus sign we have B. We have FB, which is FB cos theta plus RB2x minus FB cos 60 degree minus RB2x equals to 0. So RB1x plus RB2x equals to FB cos 60 degree minus WT. So FB cos 60, as we know from previous calculation, is 115.5 and WT is this 294. So the answer is minus 178.5 Newton. The second thing is to take the moment about point B1 equals to 0, taking anti-clockwise as positive. So we have to take moment about this point, which is point A or B1, whatever you talk about. So the moment can be written as FB cos 60 into the distance between FB and I1BX, which is zero point 0.2, and it's anti-clockwise direction. So R FB cos 60 degree into 0 0.2. That will be your one moment with the positive sign. The second moment is due to this WT, which is WT into this distance, which is clockwise. When it is negative, so WT is equals to minus WT into 0 0.2 plus 0 0.2. We have two distances, that is 0 0.4. So distances are just right distances, so there is no confusion. This is 200 mm, this is 200 mm, and this is 90 mm. Clear? Just in case you have to write moments, there will be no confusion at all. So the third moment is due to this RB2x, which is counterclockwise, and combine all these distances. So plus RB2x into 0.49 equals to 0. So we have to find RB2x. So RB2x equals to, so this is FB cos 60 is FB cos 60, yes. FB cos 60 is 115.5 into 0 0.2 with a minus sign, plus WT is 294 into 0 0.4 with a plus sign divided by 0.49. So the answer is 192.9 Newton. Okay. So if we know RB2x, what is RB1x? So RB1x from this equation will be equals to minus 178.5 plus RB2x. So minus 178.5 plus RB2X is 192.9. So 192.9. So the answer is 14.4 Newton. This is for horizontal plane, and what for the vertical plane? So for the vertical planes, we have to adopt the same concept. So just write here WR minus RB1Y minus FB sine 60 degree minus RB2Y equals to 0. So look at the diagram. In this vertical plane, we have one force in the downward direction and three in the upward direction. So the one is up downward direction taken as positive and rest is taken as negative. So we know that minus RB1Y minus RB2Y equals to WR minus WR plus FB sine of 60 degree. So minus WR is 89.9 minus 89.9 plus sine of 60 equals to 200. So the answer is 110.1 Newton. Similarly, and we have to take summation of forces in vertical plane equals to 0, taking downward as positive. Similarly, taking moment about point B1 with anti-clockwise is positive equals to 0. So what we have is FB1 FB sine of 60 into 0.2. Again, look at the vertical force. So we have this component FB, this force into the distance from here to here is 200 into 0.2, and that is anti-clockwise. So this is 0.2 with a plus sign. Similarly, minus. So what we have here with WR, and WR into this is the clockwise, so it's a negative. So 80 WR into 0.4, clear? And the last force is RB2Y into 0.49 equals to 0. Now you look at again the diagram, which is RB2Y, this force into this total distance, which is 0.9, 0.09 to 0.2 into 0.2, you get 0.49. So when you solve it, and again I'm not solving all the details, so what we have to find, what we'll get is RB2Y, and RB2Y here is RB2Y is equals to 47 Newton, and based on this, you using this relation, RB1Y equals to 157.1 Newton. So this is the all the forces that are applied on the shaft, all the axes. The next step in this case is to finding bending moments in both planes. So finding bending moments. And I'm just repeating my diagram here so that I do not have to flick back and forth for all these times. So we have RB1X, we have FB cos 60, we have WT, and we have RB2X. Similarly, this is for horizontal plane, and for vertical plane, this is RB1Y, FB sin 60 WR and RB2Y. So by taking moment, so this is the point, this is point A, this is point B, this is point C, and this is point D. So we know that bending moment at edge points, bending moment at point A equals to bending moment at point D equals to 0 in both planes. So at the end of these two shafts, the bending moment will always be 0. So we have to find bending moment at point B and C. So bending moment at point B is FB cos 60 into 0.2. And it's an anti-clockwise, so we have to take it positive. Into point 2 is 2.9 Newton meter. This is in horizontal plane. Similarly, bending moment at point P, if we call it as x and x, sorry, bending moment at point B, point C, and that is equals to Wt into 0.09. So Wt is again just to look at the equations again. So Wt is 294. So Wt is 294 into 0.09. Well, just to verify, we have to do calculator again. Using the calculator, just to multiply again, 294 into 0.09 is 26.5 Newton meter. Similarly, this is for horizontal plane. For vertical plane, again the endpoints moments are 0. So the moment at point again A, B, C and D. So the bending moment at point B, Y equals to FB sin 60 into 0.2. So which is FB sin 60 is FB sin 60 is 200. So 200 into 0.2 is 40 Newton meter. Similarly, bending moment at at C in y direction or in vertical plane is WR into 0.09, and this is again with the plus sign because it's an anti-clockwise. So WR based on our calculations are 89.9 into 0.09. So 89.9 into sorry. So there is a mistake here. I will just to have to calculate it again. Sorry. So taking a wrong bending moments. So the bending moment at point B is because you take bending moment at this point. So we have to use this. So RB1x into 0.2. Similarly, at this point we have RB, which is in which direction? Direction is not okay. Now upward. So this is RB1x. This is RB2x into 0.09. And we know that RB1x and RB2x is equals to RB1X is, okay, just write the equations again. So this is RB1Y into 0.2 with the clockwise direction, this is negative, and the moment at this point C is RB2Y into 0.09. So we know the value of reactions. So now this bending moment at X is 2.9 Newton meter. So where RB1X is 14.4, RB2X is 192.9. So the answer is 17.4 Newton meter. RB1Y is 157.1. So the answer is 31.4 Newton meter. And last but not the least, RB2X is 47. So RB2Y equals to RB2Y is equals to 47. So 47 into 0.09 is equals to 4.2 Newton meter. Now we know bending moment each point. Now we have to find resultant bending moments at point B and point C. So resultant bending moment at point B equals to bending moment at point B x square plus bending moment at point C x square. Bending moment at point B x is 2.9 square and at C point 31.4 square. So the answer is 31.5 Newton meter. Similarly, bending moment resultant at point C is equals to bending moment at point B, which is 17.4 square, plus bending moment at point C is 4.2 square. That would be equals to 17.9 Newton meter. So last step in this problem is to find the diameter at all points. So we know that we have point A, we have point B, we have point C, and we have point D. At point A, we know the bending moment is 0. So we use generic relation that we have developed before, 16 into moment square plus torque square under root divided by pi tau allowable. So we know that here there are no moment equals to 0. So the diameter equals to cube root of 16. The torque is 39.1 because only torque is applied at this point into power into pi into tau allowable. Okay, tau allowable, if you remember from the first few slides, we know that it's either 0.3 of sigma y or 0.18 of sigma u, whichever is less. So tau allowable 1 is 0.3 of the sigma u given in the problem is 620. So that is sorry, 0.3 of sigma y, sorry. So sigma y 0.3 of sigma y is equals to 415. So the answer is 124.5 mega. So tau allowable 2 equals to 0.18 of sigma u, and sigma u is 620. So the answer is 1116 megapascal. So because of the less value of this, we have to use this value, which is 11.6. Okay, so here the idea is to use pi tau level, which is 111 into 10 to the power 6. If you solve it, the answer will is actually calculated in meters. You have to convert meters to millimeters. So the I'll just write answer in meter, which is 0.0121 meter. So you can approximately it as 12.1 millimeter. At point B, the d is equals to cube root of 16 into, now what is the bending moment at point B? Total bend is 31.5. So 31.5 square plus torque is 39.5 square divided by pi into 1116 into 10 to the power 6. So diameter based on this formula is nothing but 13.2 millimeter. At point C, the diameter is cube root of 16 into, now the moment at point C as from the previous case is this, which is 17.9. So 17.9 square plus torque is 39.5, 39.1 I think so. The torque is 39.1, sorry. 39.1 square divided by pi into 111 into 10 to the power 111.6 into 10 to the power 6. So this is pi into 111.6 into 10 to the power 6. So for point C, the diameter will come out to be 13 mm. And for the fourth case, because again there is no moment at this point, so diameter will come out to be 12.1 mm. So this is how we can have to calculate the diameter of shafts at all points. To summarize this, the problem is solved. First, draw a free body diagram by actually determining the forces of the elements like gears, pulleys, or sprockets. Based on these force direction, you have to draw reactions and then find the magnitude of all the forces. The next step will be to find the moments, bending moments based on these forces. Sorry, find the reaction forces. After find the bending moments, and after finally from the bending moments, we have to find the diameter. So this is how we have to solve the shaft problem. This notes will be provided to you along with this video lecture. But going back to the slides, we have another problem in which I will try to upload the solution. In which, if you look at the problem, in which we have the, if I just quote here, if you look at this, so we have the two bearings here, C and D, and we have a pulley chain sprocket at here, and we have a gear. Now this gear is horizontal. So again, remember, so you have all the values are given, pressure angle is given, RPM is given, diameters are given, sprockets are given. So the method is exactly the same as from the which is this problem. Exactly the same as we have solved it. The only difference is now elements are actually on the corners and bearings is in between. So practice those problems. If you practice these two problems, so I will again give you one or two more problems in the slides so that you will able to solve it. So this is how we actually have to design the shaft diameters. Hopefully you have enjoyed it, you have understood it. If you have any questions, because in the last week we are going to have presentation, so it will be difficult to have class discussion on this topic. But you have any problem, please do ask me, come in my office. Although I'm busy these days, but you can still find time to come to me. And the last but not the least, the one correction that I have to make, and that's very important, that when I'm teaching this topic to section B, there will be a mistake in the WT and WR directions. So for section B students, please correct those directions. I have actually drawn this direction wrong in the class. The WT direction will be tangential, which is passing through tangent, and WR will be radial, that will be going toward the shaft. In the class, actually to flip those forces. Yes, there will be a slight difference in the diameter, but in the problems, please do correct the triangles. The gear triangles will be the component that is going through the tangential will be WT, and the component that is actually applied to the radial is actually WR, and rest will be calculation will be the same. So hopefully you have enjoyed it. We have got the last topic. I will upload the last topic video lecture last topic very soon. Thank you very much for your time. Allah Hafiz.